Alright, we're going to start getting ready to talk about the Ceil theorems, but before we do that, we're going to have to talk about p-groups. So, what is that? Let's see here. So G is a p-group if, well, obviously G has to be a group, but the important thing about this group is that its order is p to the k for some positive integer k, which is not 0. Well, no, it's not 0. So, what can we say about these p groups? Well, if G is a p group, and let's see here, we have G acting on a set X. So this is going to be a finite set. So G is acting on a finite set. Then the size of X is equivalent to X to the G mod P. Where we haven't defined this set yet. X to the G is, well, it's sort of, you can guess what it would be. I'm just going to, for the sake of space here, just write this as the intersection overall G and G of X to the G. Let's write it out. So then, for all G and G, Gx equals X. So remember, X to the little g, that's going to be the collection of points in X that are fixed by this little g. But if we take their intersection, the intersection over all of these, then that's going to give us a collection of X's which are fixed by every single G and G. And so that's how we define this intersection. And the size of this set will be equivalent to the size of X mod P. So this is actually not too difficult to prove. So what we do is, we know that the size of X, and this is going to be from a previous result, this is equal to the sum over all, did I put that right? Yeah. The sum over all representatives from conjugacy classes, no, orbits. These are, let's see here, alpha is, okay, well no, alpha is not a representative. Alpha is an orbit, given by, an orbit in X given by this group action. And then we're going to take the order of the orbit under this action. I think we could just call this the size of alpha, because does that make sense? Because, right, X alpha is just some representative in X of this orbit X in alpha, of this orbit alpha in G slash X, the collection of orbits in X. And then, obviously, if you take the orbit of this, then by definition, that's just going to give you all of alpha. So I think you could just call that the size of alpha, but I don't know, for whatever reason, we don't write that here. I guess you could, but this sort of makes it a little more obvious what's going on. You actually see, okay, so this is actually an orbit, because this is the number of elements of the size, the number of elements in the set of elements of the form G times X alpha, where G is in capital G. So anyways, so we know this, but now we can write this. Some of these orbits have just one element in them. And let's see here. So let's write that out. This is sum overall alpha in G mod X, such that size of alpha equals 1 of G dot X alpha. I thought I was going to be able to fit this all on this line. But anyways, you add the alpha in... No, there shouldn't be norms around this. This is just alpha in here such that the size of alpha equals 1. So this is all alpha in here such that the size of alpha is greater than 1 of G dot X alpha. Okay, well, if the orbit is 1, then this is just the number of orbits in this set. And so if we look at the collection of all elements alpha such that its orbit has size 1, it means if you look at the collection of elements of the form that element times G, then it's just going to be the same element. And so that means precisely that it's going to be in this set. And conversely, any element in this set is going to have an orbit of size 1. And so therefore, this is equal to the size of x to the g plus the sum overall alpha in G mod X, such that the size of alpha is greater than 1 of G dot X alpha. Okay, so now we sort of see where we're going, because we have size of x is equal to size of x to the g plus something else. So if p divides this, then we're done. Okay? So let's see here. If the size of alpha is greater than or equal to 2, well, if it's strictly greater than 1, I'll just keep with that because that's how we've been writing it before. Then g times x alpha, this orbit is going to divide the size of g, but that's equal to p to the k for some k, because g is a p group. See here. And so, the sum overall alpha in G mod X, alpha greater than 1 of G of X alpha, this is the sum of a collection of numbers which divide P to the K. And so every single thing in G times X to the alpha is going to be of the form P to some power, where P to some power less than or equal to K. And so then this is equivalent to 0 mod P. And so X is equivalent to X to the G mod P, because you just look at this equation and you've got this thing is equivalent to 0 x norm x to the g plus the sum is equivalent to norm x to the g mod p, and this thing is equal to x, and so we get the desired result. Okay, so that's an interesting lemma, and now we've got another lemma. So, and let's see here, this is actually kind of a neat proof. If n equals p to the rm, where p is prime, and I'm going to write p does not divide m. You could also say that p and m are relatively prime, or like their greatest common divisor is 1, but this is a little more intuitive for me, but of course they're all equivalent statements. Then n choose p to the r is equivalent to m mod p. And this actually comes from a Bourbaki textbook, I believe, which is actually kind of an interesting collection of mathematicians, so you can go on Wikipedia and read about them if you want. But anyways, so we're going to start with the set group G, which is Z mod PZ. And T be some set of size M. So we're going to just call it, so it's a set with M elements, so we'll just call them A1 through AM. And what these look like, I really don't care. All I care about is that there's M of them. Okay? So let X be G direct product with T, just as a set. And we're going to define a collection script E, or I don't know, squiggly E. And this is going to be the collection of subsets of X that have size P to the R. So Y and X, just such that the norm of Y is, or the size of the set Y is P to the R. Okay? So let G act on X by GHA is going to be equal to GH comma A. And you can just see that this is a group action because all you're doing is you're just doing the group operation in that first coordinate and just leaving the second coordinate fixed. If you want to write out the details to prove that this is a group action, you can, but once you start writing it out, you see, oh, it's kind of obvious. You just do the obvious thing and it just works. Okay? So given this group action, we have G acting on script E by, let's see here, if we take G acting on, let's see here, if Y is equal to Y1 through Y P to the R, where, let's see here, so Y is just some subset of X of size P to the R, so we'll call those elements little y. So each of these little yi is going to be of the form H comma A for some H and G and A and T. And so this is going to be just, we let G act on each of these individually. And so obviously, since this is a group action, this is going to be a group action as well because we're just letting it act on each of these individually. Although I guess it isn't completely obvious here that you're going to get another group of another set of size P to the R. Like maybe when you do this, some of these will become the same thing. But let's see here. If GYI equals GYJ, then you just apply G inverse to both of them, and then you'll get YI equals YJ. And so since all of these are distinct, all of these must also be distinct. And so I guess it is sort of obvious that this is a group action, but it's important to think about that, to realize, oh, we got to make sure that applying this group action to this element Y in script E gives us another element in script E. So like even if the group action itself behaves well, like you say that the group action is associative and that E fixes everything, you still got to make sure that things are getting mapped to the right places. Okay? So if we can prove that the size of E to the G is equal to M, then what's going to happen? Then we know by the last lemma that the size of E is equal to the size of e to the g. No, it's not equal. It's equivalent to the size of e to the g plus p. That's not right. That's not right. Ignore that. I did not write that in there. This is equivalent to this mod p. That's what I meant. Okay, so those two are equivalent mod p. But what is the size of E? Well, the size of E is just the collection of things. Well, here, let's start with X. What is the size of X? The size of X is just the number of elements in G times the number of elements in T. And so the size of X is equal to P to the R times M. And what about the size of that other thing? What was the other thing? The size of script E. Well, if you have a set of size here, and we're going to call this, right, this is N. So how many subsets of a set of size n have size p to the r? Well, the definition of that number is just n choose p to the r. Right? And so what this statement becomes is n choose p to the r is equivalent to, let's see here, if e to the g is m, so this is equivalent to m mod p. And that's exactly what we're trying to prove here. And so what we want to prove, that this set has size m. Okay, well, m happens to be the size of t, so you might think, oh, well, maybe the elements of y only depend on that element of t. So that actually turns out to be what we do. So let's see here. So to prove that script e to the g equals m, we're going to choose some element basically for all j between 1 and n, or m, let yj be the collection of all elements of the form g comma aj. And of course, this set, really what I should write is like yj equals the collection g comma aj, and then a colon, and then write little g and big G. But for the sake of space, because I clearly don't have it down there, I'm just going to write this. So this is a collection of all, like, any little g and g, and you just put aj with it. And so we want all of these to be precisely the set e to the g, because there's obviously only there's precisely m choices of yj. Okay, so let's pick some hat in y. Well, actually, first we should choose a y. So let y be in script e to the g, and then pick some element h comma at in y. Then if we apply any element g to this, it's also going to be in y. And so what that tells us is that yt is contained in y. But look at yt. Just by definition, the size of yt equals p to the r. And p to the r, of course, is equal to the size of y. So y equals yt. So every element, therefore, I gotta hurry up. Every element of of script e is of the form yt, where 1 is between m, so the size of e to the g is equal to m. And so there we go. That's exactly what we need to prove in order for the proof to work, and we proved it, and therefore the proof works. And so now we're done.